on the other hand, the geometric description of that kind of phenomena, that kind of a twist, is well described. It's called a flat bundle, or a connection, or a flat connection on a bundle, one of these fiber bundles that would take me too long to describe. So that made me realize, hey, here's this remarkable phenomenon in physics, which mathematically is trivially described by using modern mathematics. And I told this to a few of my other mathematical friends, for example, Singer from MIT, who communicated, and he got excited, and he communicated this to Atiyah and some other very prominent mathematicians with whom he was working. And so they at least began looking at some of the issues in physics that their approach to geometry and topology could be applied to. I think at the same time that Frank and I were talking, I expect there were others who were having the same kinds of discussions. I don't think we were unique in getting this going. It was the time was ripe, and so I'm sure there were others who were getting involved. Within a few years, I decided to try to make some money, and stopped.
How'd that work out for you, by the way?
Fine.
Good. Sorry. Go ahead.
You didn't ask Jim whether his ability to make money is related to geometry.
Yeah, you could ask me that.
And I intend to.
And it isn't.
I was wondering whether you had discovered some secret formula.
No secret formula
for producing things in the marketplace. Well, to get back to the center which you are funding, what do you expect out of that?
I expect good science. I think because of the focus, we have a chance to see some very interesting developments there. I think I did it for one thing because, or we did it because we wanted to make a gift to Stony Brook. I feel Stony Brook gave us a lot, and we were going to make a gift to Stony Brook of some sort or another in connection with their capital campaign. But this subject I began to realize this would be an excellent thing to use that money for. So we focused on this, and I'm hoping great results come, and a lot of people get trained, and it becomes a fount of knowledge in this area.
And you must be very interested in that.
Yeah, please allow me to supplement what Jim said. From the physics side, in the 20th century, starting with Einstein, Heisenberg, Bohr, through several revolutions, there was great progress. However, there is one nagging, difficult problem, and that is how to put gravity and the quantum mechanics together. Gravity and quantum mechanics are both essential theoretical and experimentally important ideas and concepts, and the theory behind them must be put together, otherwise the whole of physics is sort of not exactly matched up. But we met with great difficulties in putting the two together, and this is the main subject in fundamental theoretical physics in the last 30 years. And in the last 30 years, one bright idea took place. It's called superstrings, or string theory. So string theory now attracts, I would say, at least 1/3 of all the brightest young PhDs in theoretical physics. It is the hottest field in the last 30 years. And string theory is deeply entangled with deep mathematics, and especially with deep geometrical and topological mathematics. And that must be one of the reasons in the back of Jim's mind in funding this center, because this center would concentrate on deep geometrical, topological problems, which many of which came from the string theorists. So I would presume that when they make appointments in the center, there would be people who would be working in geometry, who would be working in string theory, and who would be working in between the two.
Those are the appointments you'll be making?
Primarily. There'll be, there'll be a faculty of 7, a director and 6 faculty members, permanent members, and then about 30 visitors every year. And many of the visitors, and perhaps most or even all of the faculty, might be as Frank described. But there'll be other, and always have been, strong interactions between even the geometric side of mathematics and physics. So I think we don't want to be known as a string theory institute per se. String theory has come. There may be other theories that develop along the line, and we want to stick to, I think, the geometrical side of things, which is a very, very broad statement. But string theory and those problems in physics that relate to that, which are going to be many, right now string theory is, as Frank says, the hot thing. But it's morphing too. I mean, what was string theory 20 years ago might not be recognized. I mean, it's developing, and there are experiments now being done in the new collider at CERN when it opens. I don't know if you know about this huge accelerator that will go online next year, maybe. I'm not sure.
Perhaps if they do not get more funding problems.
Okay, well, I ran to the rescue of Rick, but I don't think I'm going to run to the rescue of CERN, so they're going to have to figure that one out for themselves.
You ran to the rescue of the one at Brookhaven National.
Yeah, I did.
You did.
But CERN is of a high enough energy, and Frank can obviously say much more about that than I, but that at the edge of those energy levels, certain conjectures, I think supersymmetry is one, might be verified. So certain things in modern physics, in particular in string theory, might have some experimental justification as a result of experiments there. Frank, you must be able to say more than...
Yeah, well, we are all looking forward to what will come out of what is called the LHC at CERN, which probably would come working, if not this year, next year. And one of the crucial questions is whether they will find a particle called Higgs particle. The good thing about it is that
Higgs,
Higgs is an Englishman. If they find the Higgs particle, it will be very good. If they do not find the Higgs particle, in my opinion, it will be even better. Why? Because all the theories converge to the Higgs particle, and if it exists, everything is smoothed out. Everything is very good. If it doesn't, it means that we are going the wrong channel. We have to completely rethink. That means there may be a revolution coming. So in many senses, that is even better. But anyway, it's
Frank's a revolutionary. He likes revolution for its own sake.
No, but the reason Einstein is so famous is because he personally created 2.5 revolutions. So if you talk to a bright young physicist, he would like to have more revolutions rather than not. But anyway, the CERN event is a very important one. So we are all looking forward to that. No matter which way it turns out, it means that we will have more material to think about, and it's clear that those material would be in between would be in between geometry and physics.
And it will prove it one way or the other when it.
Yes.
Yeah, that should. And there are other things too, I think, that are other results that could, I think there's a lot that could come out of CERN.
Have they already asked you to rescue them?
No,
Not yet.
no. I'm not.
Don't be opening the
I'm not
mail.
advertising my availability either. That's a big project.
Let somebody else open your mail for you.
I want to say something about what Frank said about geometry
Yes.
dictating things. As Frank said, the general relativity said, look, the universe, four-dimensional universe, including time, has a shape to it. It's not flat. It has a shape, and that there's more bending in the presence of more mass and less bending in the presence of less mass, and that bending is what causes things to come together, like rolling down a channel or something like that. So the geometry forces the physics, or in a sense determines the physics, and that's, as Frank said, you know, it was a fabulous development. Now, those are very macro things. You're looking across billions and billions of miles and so on. So now, if you go to the opposite time, space scale, look very, 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 very small. Look at distances of, you know, 1/10 with 30 zeros, really small. There may be geometry going on at that scale. There may be some interesting geometry at that scale. In fact, there seems very likely to be. And a scale that is undetectable, obviously, as we're sitting here by us, but nonetheless, there may be something going on way, 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 way down there. So that I think it was Wheeler who first sort of hypothesized maybe space is sort of a foam-like thing. And at the very smallest space scales, there may be little bubbles or this, that, or the other thing. To the extent that something like that is true, then you might end up with a situation where the microgeometry of space drives quantum mechanics or some of the other physics. So it's possible that Einstein's dream or Einstein's approach to geometry explaining the physics could even end up at the micro scale. And again, I emphasize, I really mean a micro scale. That the geometry there could also perhaps simplify or drive the physics. You have a thought on that?
Yes, in general, there's some speculation about this. As I said, there's the question of how to marry gravity with quantum mechanics. And when you talk about that, these extremely small regions immediately come into play, obviously. How that is going to play out is everybody's speculation. And that is deeply entangled with this string theory also.
For sure, for sure.
I wanted to mention one thing about your background that came to mind when we were describing Dr. Young as a revolutionary here, but which was your getting fired from the government, which was pretty much the reason you came to Stony Brook to begin with. Tell me about that.
Well, it was simple enough. I was at I'd spent 4 years in Princeton at something called the Institute for Defense Analyses, which was a place that specialized, was a government agency or contracted to a government agency, the NSA, in fact. And they hired mathematicians there to work on very high-level, secret, obviously, codes, try to help the United States make more secure codes and try to crack Russian codes, for example, and so on. They hired mathematicians, but the deal was you could spend half your time doing research on your own and half your time working on the government problem, so it was nice. And I took that job for a variety of reasons, went to Princeton. And I was an okay code cracker. And I also did a fair amount of mathematics while I was there. In fact, the work that I did there justified Stony Brook giving me that offer because I had solved an old, well-known problem. But in the meantime, I was, you know, being a code cracker. And, but the Vietnam War was heating up and I didn't like it and I was outspoken about it. We weren't doing any work that impinged on the war. We were working on very high-level Russian cipher systems, and I think there was no application at all to Vietnam. My view was it was a dumb place for us to be, and we ought to get out of there.